Welcome to this lecture on the Carnot cycle for conversion of thermal energy to work. In this lecture, you will learn why the thermal efficiency of a nuclear power plant is limited and how we could possibly increase this efficiency. My name is Jan Kloosterman and I work at the Faculty of Applied Sciences of Delft University of Technology in the Netherlands. Nuclear power plants, like the one shown here, need large cooling towers to expel their waste heat to the environment. But why is the efficiency for conversion of thermal energy to electricity so small? Why can't we convert heat to useful work with 100% efficiency? The reason for this is that the laws of thermodynamics simply prohibits this. But what exactly is the background of these laws? What is the real limiting factor in the thermodynamic efficiency of thermal power plants? After this lecture, you will understand the thermodynamics behind this phenomenon and you will be able to explain to others why this environmental burden in thermal power plants cannot be avoided. To this purpose, we will derive the most efficient power conversion cycle possible, the Carnot cycle, and we will demonstrate that the maximum efficiency of the Carnot cycle for realistic cases is no more than 50%. But first we have to go through some basic concepts of thermodynamics. In thermodynamics we distinguish three kinds of systems. The open system, in which both heat and mass transfer to and from the system is possible. The isolated system, in which no transfer at all is possible, and in between the closed system, in which only transfer of heat is possible. The open system is often studied in the field of chemical processes, which requires a continuous flow of chemicals and heat to and from the chemical reactor. The closed system is a typical case studied in the framework of thermal conversion cycles. In this case, heat is added to the system and work is done by the system. Imagine we have a cylinder filled with some working fluid, gas in this case. If we heat up the gas, we know from experience it will expand and it will push the piston upwards. In this case, heat is transformed to work. If you write down the energy balance for this situation, we have the heat added to the system at one hand, this is delta Q, and the increase of the internal energy dU and the work done by the system delta W at the other hand. On the next slide we will explain the concept of internal energy. Know that in this version of the energy balance, which is actually the first law of thermodynamics, we have a real differential for the internal energy U, but increments for the work and heat. The internal energy is a real state function of the gas, which means that it is uniquely defined between two operating points of the gas, independent of the path taken between these two states. For the work and the heat, this is not true, because we can never know how much heat we have to add to the system and how much work can be done by the system between two states. This depends, for example, on the friction between the piston and the cylinder and other irreversible processes. Note that the work done by the system equals P dV for a reversible process. For the remainder of this lecture, we will assume that a gas behaves like an ideal gas, which means it consists of point particles with no other interaction than elastic scattering. In this case, we have a simple and unique relation between the three state variables of the system, pressure, volume and temperature, as shown in the formula on this slide. The internal energy of the system is the sum of all kinetic and potential energy associated with the random movement of the particles in the system. For an ideal gas with no forces between the particles, the internal energy consists of kinetic energy alone. Assuming an ideal gas, we can derive from statistical physics that the energy distribution of the particles is Maxwellian shaped and that the average energy per degree of freedom equals 1/2 kT. The number of degrees of freedom depends on the complexity of the gas molecules. For monoatomic gases, atoms can only move in x, y or z direction, and the number of degrees of freedom is 3. Diatomic gases can also rotate around the two axes perpendicular to the axis connecting the two atoms, and the number of degrees of freedom increases to 5. Note that in this case the rotation around the axis connecting the two atoms and the vibration mode in which the two atoms are moving towards and away from each other is usually not counted as a degree of freedom in this formula, as these modes become only significant at very high temperature. More complex molecules can also rotate around the axis connecting the two atoms, and the number of degrees of freedom increases to 6 in this case. From the first law of thermodynamics, shown here on the slide, we can easily deduce that the heat added to a system at constant volume adds up to the internal energy with the same amount. The work done at constant volume is indeed 0. We will now introduce a new state parameter that combines the internal energy and the work done by the system. This is the enthalpy, which equals the sum of the internal energy U and the product of pressure and volume. The enthalpy is a handy parameter for processes occurring at constant pressure, like chemical processes in contact with the open air, because at constant pressure the heat added to a system leads to an increase of the enthalpy with the same amount, as shown on the slide. We now define the heat capacity of the gas by the amount of heat needed to increase the temperature of the gas with 1 degree. Of course, it will make a difference whether this is done at constant volume or at constant pressure. At constant volume, the gas cannot expand and all heat added to the system adds up to the internal energy of the system and thus leads to an increase of the temperature of the gas. If the pressure is constant, the gas can freely expand and part of the heat is also converted to work without increasing the temperature. The heat capacity at constant pressure is therefore always larger than the heat capacity at constant volume, with an amount equal to the amount of gas in moles times the gas constant, shown in red on the slide. Note that this relationship only holds for an ideal gas. The ratio between the two heat capacities is called gamma, shown on the slide, which is always larger than unity. Of course, this relationship is only valid if the derivative du dt at constant volume equals du dt at constant pressure. This will be shown on the next slide. Now we will prove that the derivative of the internal energy with respect to temperature is equal under the condition at constant volume to that at constant pressure. Because the internal energy depends on two state variables only, we can take the full differential of the internal energy with respect to temperature and volume, as shown on the second line of the slide. If we now take the derivative du dt at constant pressure and use the fact that du dv at constant temperature is 0 for an ideal gas, we can easily show that the derivative of u and t at constant pressure is equal to that at constant volume. Before we can design the most efficient thermodynamic conversion cycle, we have to derive the relationship between pressure and volume for two transition processes. The first one is a process at constant temperature. Using the ideal gas law, we know that the product of pressure and volume is constant in this case. The second process is an adiabatic one. This means that there is no heat exchange with the environment. In this case, we first express the first law of thermodynamics in terms of U and H, as shown in the black formula. The ratio of Cp and Cv equals dH divided by du, which results in the red formula on the slide. Integrating the red formula gives the result shown in blue, from which we can derive the final relation between pressure and volume for an adiabatic process. This relation is shown in the second black box on the slide. We will now derive the various steps in the Carnot conversion cycle and plot these steps in a so-called PV diagram with the volume on the x-axis and the pressure on the y-axis. Note that in such a plot, the area under the curve corresponds to the work done by the system or the work done performed on the system. We will do this for an arbitrary quantity of 1000 moles of an ideal gas with a value of gamma of 3.7. We will start our cycle at point 1, indicated in the plot. From this point, we could start with any step we want, like expansion or compression. However, we choose to start with the power conversion step, in which heat is added to the system and work is performed by the system. The most efficient power conversion step is the one in which the heat delivered to the system is completely converted to work, without any increase of the internal energy of the system. This means we follow an isothermal line through point 1. Here the isothermal line through point 1 is shown, which we will follow to the right. We have to stop the isothermal expansion of the gas at an arbitrarily chosen point 2 on the isothermal line T high. Because we expanded the gas at constant temperature, the internal energy of the gas did not change. This means that all the heat supplied to the system is fully converted to work with 100% efficiency. This is indicated with the red arrows Q and W, which are equally large in this case. In the PV diagram, the work done by the system is equal to the area under the curve, indicated with the red area shown here. After the fluid has expanded to point 2, we have to pump the working fluid back to point 1 if we want to have a cyclic process. If we would do this along the same red line in the plot, we would have to deliver as much work to the system as we have extracted, and no net work would be left. Therefore, we will express the gas at the lower temperature, which is much more efficient. If we do this at the lowest temperature possible, which is the temperature of the environment, we will achieve the highest efficiency for our cyclic process. To compress the gas, we have to pump it from point 3 on the isothermal line T low to a point left on this curve. This is one of the two compression stages to bring the working fluid back to point 1, and it requires external work, indicated here with the blue arrow W, which is fully converted to heat. This heat needs to be expelled to the environment to keep the temperature of the gas at T low. This heat flow is indicated with the blue arrow Q. Again, these two arrows are equally large, because the temperature remains constant in this step. Likewise, with the expansion stage between points 1 and 2, the work done on the system between points 3 and 4 is the area below the curve, indicated here in blue. Now we have to connect points 2 and 3, such that we achieve a maximum efficiency for the whole cycle. Because the temperature between these 2 points drops from T high to T low, also the internal energy of the working fluid reduces. For an ideal gas, the internal energy is proportional to temperature, as we have seen before. Therefore, we connect the 2 points with an adiabatic line, which implies that there is no heat exchange with the environment. And in this case, the internal energy of the system between points 2 and 3 is fully converted to work, without production of waste heat. On the left part of the cycle, we have to connect points 4 and 1 to close the cycle. This part requires external pumping power as well, or heat to increase the temperature and thus the internal energy of the gas. Because we go from T low to T high, the internal energy should increase as much as it was reduced in the step between points 2 and 3. If we connect points 4 and 1 with an adiabatic line as well, we do not lose any external pumping power to waste heat, and also this part of the process is most efficient. Note that the work done by the system between points 2 and 3 is exactly equal to the work done on the system between points 4 and 1. The area under the curve 2 to 3 is therefore exactly equal to the area under the curve 4 to 1. Because the net work done by the fluid or done on the fluid in each step is equal to the area under the respective curve, the net work done in one complete cycle is equal to the net area enclosed by the cycle. This is indicated here with the green area, shown in the slide. Before we derive the efficiency of the Carnot cycle, we need to derive an expression for the total work done during an isothermal expansion step. The work done is pressure times the change in volume, integrated between the 2 points. Using the ideal gas law, we obtain the upper expression for the isothermal expansion step and the lower expression for the adiabatic expansion step. We will use the upper expression to calculate the efficiency of the Carnot cycle on the following slides. The lower expression is actually not needed, because we already know that the work done by the system between points 2 and 3 equals the work done on the system between points 4 and 1. These two contributions cancel in the calculation of the efficiency. The efficiency of a specific heat conversion cycle equals the net work done divided by the heat input. Using the expression from the previous slide, we can derive the result that the efficiency equals 1 minus T low divided by T high. Of course, this is only true if the ratio of V2 and V1 equals that of V3 and V4. This we will prove on the next slide. Now we will prove that the ratio of V2 and V1 is equal to that of V3 and V4. First note that for the isothermal lines, the ideal gas law gives the relations at the points 1 to 4, as shown in the black formulas on the slide. The points 2 and 3 and the points 1 and 4 are related via the adiabatic lines, which lead to the relations in blue as derived before. Substitution of the black formulas in the blue ones give the relations in red. And dividing the two red lines gives the equations in magenta, which proves the relation we were looking for, namely that the ratio of V2 and V1 equals that of V3 and V4. This formula gives the relation for the efficiency we have derived before. We could, however, define the efficiency of a power conversion cycle also as the ratio of the net heat converted to work and the total heat input. This leads to an expression for the efficiency equals to 1 minus the ratio of the heat expelled to the environment, Q low, divided by the heat input to the system, Q high. From the comparison of the two expressions, it is clear that the ratio of the heat transfer and the temperature at the high temperature input stage must be equal to the same ratio at the low temperature output stage in a reversible power conversion cycle. The ratio of the heat flow and temperature is equal to a new state parameter called entropy. In a thermodynamic cycle, the entropy of the system cannot accumulate indefinitely, and heat input at high temperature should always be accompanied with heat expelled to the environment at low temperature, with the difference between the heat input and output available for work done by the system. In case of an irreversible cycle, heat is produced in the system itself due to friction, turbulence or other irreversible processes. This leads to extra production of entropy, which has to be removed from the system as well. Therefore, in irreversible processes, more heat has to be expelled to the environment and the efficiency of the power conversion cycle goes down. On this plot we have shown the Carnot cycle once more on the PV diagram. Heat is input to the system at constant high temperature. This is the red arrow in the plot, and heat is extracted from the system at a constant low temperature, which is the blue arrow in the plot. Also work is done by the system, this is the black arrow on the right, and an equal amount of work is done on the system, which is the black arrow on the left. The heat added to the system divided by the temperature T high equals the entropy added to the system, while the heat removed from the system divided by T low equals the entropy removed from the system. Entropy cannot accumulate it in the system, so the entropy added to a system must be equal to the entropy removed from the system. In this plot we have shown the Carnot cycle in a TS plot, temperature versus entropy, with the entropy along the x-axis. The two stages involving heat flow also lead to a change of the entropy of the system. While for the two stages where only work is done, the black arrows only lead to a change of temperature of the gas, but not to a change of entropy. We can finalize this presentation with a number of conclusions. First, the Carnot cycle consists of two isothermal processes, one at a high temperature and one at a low temperature, connected by two adiabatic lines. Second, the net work done in a cycle is equal to the area enclosed by the curves on the PV diagram. Third, the Carnot cycle is the most efficient thermal conversion cycle possible. And fourth, the efficiency of the Carnot cycle equals 1 minus T low divided by T high. For a nuclear power plant with a maximum coolant temperature of around 330 degrees Celsius, about 600 Kelvin and an environment at about 300 Kelvin, the maximum efficiency would be around 50%. In reality, because the ideal isothermal and adiabatic processes cannot be achieved in practice, the efficiency is only around 35%. Thank you for your attention. And if you have further questions, please contact us at one of the websites shown here.